Hi everyone. In this session I'll be talking about a special discrete random variable called the binomial. It has its own specific name because it appears very frequently in practice. It's an experiment that has certain properties that enables us to identify that experiment, and because it is so common, it has results that is readily available as well as probability tables, which makes it easy to work with. Now, as usual, the outcomes for this session: you must always know the definitions, you must know the properties of a binomial experiment, you must be able to solve binomial problems using tables. You can also solve it using certain apps that has the binomial distribution available. You can also solve it using Excel if you so wish. You must be able to calculate the parameters for a binomial distribution, and you must, very important, be able to solve word problems for the binomial. Now, let's consider an experiment where the same trial is repeated n independent times, okay, like flipping a coin. The first flip will not affect the second, and the second will not affect the third, and so forth. Okay, so it's the same thing being repeated a given number of times. Secondly, each trial can result in only a success or a failure. So if I'm flipping a coin, then I might say that heads will be considered a success. Somebody else might say tails will be considered a success. But the point is, there's only two possible outcomes, and one of them I will be interested in, the other one I will not. So the one of interest, I'll call that a success. Then, the probability of a success will be denoted by a lowercase p, and the probability of a failure will be denoted by a lowercase q, which is equal to 1 minus p. Because we only have two outcomes, a success or a failure, it means that if we take the probability of a success and we add it to the probability of a failure, we must get 1, because the 1 represents 100% of the outcomes. We only have success and failure. So if we have these properties in our experiment, then we can say let x be the number of successes in the number of trials n, and then we'll say x is a binomial random variable with parameters n and p, where n will be the number of times that you repeat this experiment, and p, of course, as I just said, will be the probability of a success. The way in which we denote it will be capital X with this tilde. This little wave is called a tilde. Lowercase p to indicate binomial, and then in brackets n and p. Random variable parameters are always given in brackets next to the abbreviation of the random variable. So b means binomial, and we identify this binomial by looking at n and p. Right, the PMF for my binomial is given by this function over here. Now you should recognize this first term, this first part. It's n combination x. So n is the number of times that you repeat the experiment. X will be the number of successes that you are interested in. P is the probability of a success. That will be to the power x. 1 minus p, or q, will be to the power n minus x. And of course the number of successes can start at 0, but it must end at n. If we repeat an experiment, let's say 5 times, we can fail every single time, which means the number of successes is 0, can't be less than that. But if we repeat the experiment 5 times, it also means that the maximum number of successes will be 5, which is the number of trials, n. Right, now the mean for x, of course, is denoted by mu, and it's calculated simply by taking n times p. So that n times p, that will give us the mean, and the variance, easy enough, will be n times p, which is the mean, times 1 minus p, which is q. Now, before we move on to some examples, let's just have a look at the effects of the parameters on the distribution. Now, the parameters determine the shape, the size, and the location. So we're going to still be looking at the binomial. Now, let's consider a binomial PMF with n equal to 10 and p equal to 0.25. Now, this was constructed using Excel, and we can see here the number of successes range from 0 to 10. Because we have 10 trials, It means that we can have as little as 0 successes, but not more than 10 successes. And on the vertical axis, we have our probabilities. Now we see the shape of this is positively skewed. Now if we look at calculating the mean, we denote it by E of x, and it's simply n times p. Now in this case, n is equal to 10, p is equal to 0.25, so that means the mean is equal to 2.5. And 2.5 is situated over here. Now remember what I've said before, the mean is not necessarily a value in the data set. In this case it's 2.5, whereas the actual observations can only be integers, 0 to 10. Now if we look at the bars themselves, then we see that we have the highest bar at position 2. So that means the mode is equal to 2. Now since the mode is less than the mean, we can say that the distribution is positively skewed. So this calculation over here, the mean and the mode, and then the comparison, just confirms what we saw when we drew this distribution. Right, and it also confirms what we saw earlier on regarding the relationship between the mean, the median, and the mode, and the shape of distributions. Now in this case, we still have n equal to 10, but now we have p equal to 0.75. Now we can see from this that it is negatively skewed, because it has a longer tail on the left and a very short one on the right. If we calculate the mean, it's still n times p because we're working with the binomial. Remember, this n times p for the mean is for the binomial distribution. Then we take 10 times 0.75, and that gives us 7.5. Now 7.5 is again not a possible value, and it's sitting over there. If we look at where the highest bar is, it is sitting at position 8, so that means the mode is equal to 8. So that means the mean is less than the mode, because the mean is 7.5, the mode is 8, so we can deduce that the distribution is negatively skewed, which again confirms what we saw previously. Now in this case, if we still take n equal to 10, but now p equal to 0.5, then what do you notice? You notice that this distribution seems symmetrical, that in fact there's no longer tail on either side. So if we look at the mean, which is n times p, it's 10 times 0.5, remember 10 times 0.5, then we get 5. The 5 is sitting over there, which is also the highest bar. So that means the mode is also 5. And since the mean equals the mode, we can say that the distribution is symmetrical. Right, so in all three of these cases so far, it supports our visual assessment of the distributions. Now lastly, if we increase the sample size quite significantly, we make n equal to 50 and make p equal to 0.25, then what do we see? Well, remember, the outcomes can be anything from 0 up to 50. So this is 0 up to 50. And although it's not visible over here, we actually have outcomes sitting over here, but the probabilities are so small that they are effectively, for practical purposes, 0. Right, they'll have so many decimal values and so many zeros before you reach the actual value that we can say that it is effectively 0. Right, so what do we notice? We notice that this thing is fairly symmetrical. It's not as perfectly symmetrical as this one over here, but it's definitely not as skewed as the first one, which is positively skewed. Right, if we calculate the expected value, or the mean, we see that it's 50 times 0.25. That gives us 12.5, which is sitting over there, which is right next to the mode, which is 12. Now, the mean is approximately equal to the mode, which means that the distribution is approaching symmetry. Now, you should ask yourself, why am I saying over here that the mean is approximately equal to the mode if the difference between the mean and the mode is 0.5? But here, I'm stating clearly that there's a difference. I'm saying that the mean is less, I'm saying that the mean is more. And the difference between the mean and the mode in the top two cases is also 0.5. Now the reason why I'm saying here that they are approximately equal is because I'm comparing the difference of 0.5 to the size of the interval. In other words, I'm comparing it to n. So 0.5 compared to n, if we relate it to a percentage, then it means we multiply n by 2 to get 100. We multiply this by 2, then it is 1%. So this 0.5 is 1% of that interval. If we do the same over here, then the interval has size 10, so we need to multiply it by 10 to get 100%. So if we take the difference, which is 0.5 as well, then we multiply it by 10, then we get 5. The same in this case over here on the left. Right, so that means that that for the top two cases, 0.5 represents 1% of the interval, 5% of the interval, whereas in the bottom right case, 0.5 represents 1% of the interval. So that means, relatively speaking, which is really important, the word relative, right? Relatively speaking, we have a very small difference between the mean and the mode. Right, so what can we conclude from this? Well, in the first case, if we have a small sample size and we have a small probability of a success, then we can say that the distribution is positively skewed. In this case, if we have a small sample size, a large probability of a success, then the binomial distribution will be negatively skewed. In this case, if we take any sample size and p equal to 0.5, then the binomial is symmetric. Let me just stress that. If p is equal to 0.5, then the distribution will be symmetric regardless the value of n. And then lastly, if we take a large sample, in this case n equal to 50, small probability of a success, then the binomial distribution approaches symmetry. Now, you should ask yourself, what do I mean by a large sample and a small sample? Because here I'm saying that 10 is small, and here I'm saying that 50 is large. Well, in statistics, we usually consider a sample of at least 30 as being large. Anything less than 30 is considered a small sample. Now this is important to remember because it will be coming up in later sections. Right, let's move on to some examples now. The number of independent trials is 5. The probability of a success remains 0.25 for every trial. Then what is the probability of x equal to 2? So of course this is a binomial problem because we are given a fixed number of trials, which is 5. The probability of a success remains the same for every single trial at 0.25, and we can only get successes and failures and of course independence. Okay, so we have a binomial distribution. So what is the probability of x equal to 2? Well, we just simply substitute. So first of all, n is equal to 5. Okay, n is equal to 5, so I'll substitute a 5 in there just to show that n is 5 in the distribution. Over here I'll substitute 5 into n, and there I'll substitute 5 into n as well. Next, I have p equal to 0.25, so to show the value for p, I'll substitute it in there as well. And then here I have p 0.25 to the x and 1 minus p, so 1 minus 0.25. And then lastly, I'm interested in x equal to 2, so I'll substitute all the x's by 2. So now I have no unknown values in this PMF, and I simply solve using my calculator or whatever means you wish to use. And we see that it's 0.2637. In other words, 26.37%. This is the chance of getting a 2 when you perform an experiment 5 times, and the probability of a success is 0.25. Okay, then the probability of getting 2 successes is 26%. Let's see another one. Let's say that n is equal to 20. Probability of a success is now 0.3, and we're interested in x equal to 15. So the same thing applies. We know that this is a binomial because it's set up to be a binomial. So we simply substitute. Everywhere where we see an n, we'll put 20, so 20 in there and in there. Everywhere where we have a p, okay, which is there and there, we'll put 0.3. So we'll substitute that, and of course here just to illustrate. And then lastly, we're interested in getting 15 successes, so we'll substitute 15 in there. Okay, so now we have no unknown values anywhere in our PMF, so we simply solve once again. So you see this is very small. This is 0.0000 and a 4. So if we look at percentage, then this is 0.004%. So 0.004% is the chance of getting 15 successes when we have 20 trials or 20 experiments, and the probability of a success in each trial is 0.3. Okay, so this is a very small chance of getting 15 successes. What about if we consider x less than or equal to 15 and not equal to 15? Then we don't have a PMF anymore because we are summing. So what we have now is in fact a CDF because we are adding together all of these probabilities. Where are we adding from? We're adding from the smallest possible value 0 right up to 15. Okay, so this is saying x less than or equal to 15. So less than doesn't specify a minimum, but we go down to the minimum value that x can be, which is 0. So we'll take 0 all the way up to 15, adding it together. Now this can be a very tedious calculation because we have to do the same calculation that we just did in the previous problem. We have to do it 16 times, starting from 0, ending at 15. However, as I said in the introduction, because the binomial is a very common distribution, a lot of results are available, including probabilities, without much calculation required. So we'll see here that I simply wrote probability of x less than or equal to 15 will be 1, and this I got from a binomial table. Now what is this binomial table? Well, in the text you have this binomial table, and it is a CDF table. In other words, the probabilities contained on this table over here, these are cumulative probabilities. You will see that we have a value for n, which can be 2, 3, 4, up to 7 for this page. Okay, there are multiple pages where n carries on, gets bigger. N is the number of trials, and then x will be the number of successes. So when n is 2, in other words 2 trials, the number of successes can only be 0, 1, and 2. When n is 6, in other words 6 trials, the number of successes can be as small as 0 and as large as 6. And then here we have the probability of a success on each trial, p. 0.05 is the smallest and 0.5 is the largest. And as I said, this is a CDF table, so it contains cumulative probabilities. Now we are interested in the table where n is equal to 20. So here n goes up to 7, so we need to look for the page where n is equal to 20. So here is actually where n is equal to 20. Then we just need to look for our relevant values. So n is 20. We're interested in p equal to 0.3, and there it is. And we're interested in x less than or equal to 15, and there's 15. So all that we do, just zoom in a bit so we can see, is we check to see where all of these things intersect. So p equal to 0.3 will be for this entire column, x equal to 15 will be for this entire row, and where they intersect we have a cumulative probability of 1, and that is in fact this one over here. Right, what about x greater than 15? Well, this is very easy because we can simply say 1 minus the probability of x less than or equal to 15, right, cumulative, and that will just be 1 minus 1, which is 0. What about the probability for x equal to 15? Now we can do it using our calculation for our PMF, or we can actually do it using our table. We know what the probability of x less than or equal to 15 is, we just calculated it, it's 1. If we subtract the probability of x less than or equal to 14, then what remains is x equal to 15 once we subtract the one from the other. So going back to our table, we still have p equal to 0.3, but x is now equal to 14, so where these two rows intersect, we again have 1, so that means that this is just 1 minus 1, which is 0. Right, the next example is a little bit more practical. It says that you guess, very important, you guess the answers to a 10-question multiple choice test, where each question has 2 options. and only one option is correct. Okay, so that means we have 10 questions in the test. Okay, 10 questions in the test, and each one has two options. So only option A and B for every single one, all the way down to the last one. We guess each one. So that means whatever we guess here will not affect what we guess there, will not affect what we guess there, or anywhere in between. So that means all of these guesses are independent. Okay, so let's see what we have. Since the same trial is being repeated n times, in this case 10 times, okay, this the same style question. Since we can either get a question right or wrong, since we have the probability of a success, that is a half, because one out of the two options are correct, either A or B is correct, so guessing the correct answer will happen with probability a half. Okay, so that's the probability of a success. We have the probability of a failure. If we let x be the number of successes, then x is binomial. Okay, this problem satisfies all the criteria. So now I'm interested in scoring exactly 50% for the test. So if you have 10 questions in the test, to get exactly 50%, you need to get exactly 5 questions right. So that means I will have n equal to 10, substitute in here, n equal to 10. I will substitute p equal to 1 over 2, p equal to 1 over 2, because I have two options for every question and only one option is correct. And then lastly, I will substitute 5 because I want 50% for the test. There's 10 questions, so the number of correct trials or the number of successes must be 5. So that's where this 5 comes from. And now solving, I get 0.2461. So that means if you were to write a multiple choice test that has 10 questions, each question only has an A and a B option, then the chances of getting exactly 50% for the test is 24.61%, which is not very good. Now secondly, how many answers do you expect to guess right? Well, what do we know about the binomial expectation? It is simply n times p. N is equal to 10, p is equal to a half, multiply the two, and we get 5. So that means if we guess the 10 questions, then we expect to get 5 correct. Next question. Still have 10 questions in our multiple choice test. Each question now has 5 options. What's the chances of scoring exactly 50%? Now we've already looked at a similar type of question, so we know that this problem is a binomial problem. What we have to point out though is that each question now has 5 options. So a, a B, a C, a D, and an E. Only one of them is correct. So if you guess one of those answers, your chances of guessing correctly will be 1 over 5. Okay, 1 over 5 chance of guessing the correct answer. So now once again, we want to know the probability of getting exactly 50% for the test. So we simply say, well, that means 5 questions correct. We know what p is, so that's 1 over 5. So we just substitute. So n is equal to 10, n is equal to 10, p is equal to 1 over 5, 1 over 5, and x is equal to 5. Right, x is equal to 5, and solving that we get 0.0264. So that means that if you write a 10 question multiple choice test and you simply guess all the answers where each question has 5 options, then your chances of getting exactly 50% for the test is 2.64%, which is much worse than the previous one, which was in the 20s. But that one only had 2 options for every question. This one has 5. Right, if we were to guess, how many answers do you expect to guess correct? Well, that's just the expected value. So it's n times p, which is 10 times 1 over 5, probability of a success, and that gives us 2. So we only expect to guess 2 answers correctly. Right, let's have a look at another example. Still with the test, 10 questions, 2 options for each. Only one option is correct. The chances of failing the test. We know that this is binomial. We know that it has parameters 10 and a half, 10 trials. Probability of guessing each one is a half because we have 2 options per question. Failing the test means that out of the 10 questions, we must get less than 5 correct. So that's where this less than 5 comes from. So less than 5 means x equal to 0, plus x equal to 1, plus x equal to 2, x equal to 3, and x equal to 4. Again, we can go to our binomial table. We have to look for where n is equal to 10. So in the first column here, n is equal to 10. We need x equal to not 5. This is less than 5. We need x equal to 4. So when n is 10, we want x equal to 4 over there. And the probability will be a half because there's 2 options. So we'll be looking at that column. Okay, so that means that it will be somewhere in this column and somewhere in this row where they intersect. So it's very small, but it seems to be 0.3770. Let's just zoom in. Okay, we don't need the middle part of the table, so I'm going to take that out. So let's see. N is equal to 10, x is equal to 4, p is equal to a half, so that means 0.3770, which is correct. So the probability of failing is 37.7% if you guess each of the 10 questions and each of them only has 2 options. Right, what about the probability of passing the test? Okay, passing the test. Well, to pass 10 question test, you need to get 5 or more questions correct. Well, this is very easy. Just using the complement rule, it'll be 1 minus failing the test. We know what failing the test is, so it's simply 1 minus 0.3770, and that gives us 0.6230. So that means there's a 62.3% chance of passing the test if you guess every answer of the 10 questions where each question has 2 options. Right, the last question. It is claimed that 15% of ducks in a particular region have an infection. Suppose that 7 ducks are selected at random. Let x equal the number of ducks that are infected. Assuming independence, what is the distribution of x? And then find the probability of x greater than or equal to 2. Let's give ourselves some space to work. Now let's see. Question A. How is x distributed? Well, the ducks are independent. Okay, so that means each trial is independent, where each trial refers to a duck. Infected or not, so there's 2 possibilities for every trial or for every duck. They either are infected or they're not infected. Probability of infected is 0.15, and that remains constant for every single duck. It's the same. The number of ducks selected is fixed. It's n equal to 7. Okay, 7 ducks are selected. So that means that x is binomial, and it has parameters 7 and 0.15. Okay, because we have to check the properties of the experiment, and we see that it is binomial. Right, find the probability of x being greater than or equal to 2. Well, x greater than or equal to 2 means that we need to add the probability of x equal to 2 plus the probability of x equal to 3 plus x equal to 4, x equal to 5, x equal to 6, and finally x equal to 7. Because we have 7 ducks, so we can't have more than 7 successes. But again, this is a long calculation if you think about the binomial PMF. So why can't we just use our table? So we'll use a complement rule. Because the table is cumulative, it means that it contains probabilities less than or equal to. We want greater than, so we'll just take 1 minus the complement. So now we need to find out what is this probability of x less than or equal to 1. So again, we'll go to our binomial table, and this is the first page of the table, and we will look for our specific values. Now we see that there we have our n. We are interested in n equal to 7, okay, the yellow there. we're interested in x equal to 1. So there's x, and there's the 1 for the 7, okay, 7 trials. And the probability of a success is 0.15. So there we have 0.15, which is the value of p. Okay, so it seems like we're going to be working in the bottom part of the table. That means the middle part there can go. So if I take it out and zoom in a bit so that we can see what's busy happening, then the value that we end up with will be the 0.7166, because p is equal to 0.15, n is equal to 7, and when n is 7 we want x equal to 1, so it's going to be this row and it's going to be this column, and they intersect at 0.7166. So we simply replace or substitute 0.7166 in here, and we subtract. So that means there's a 28.34% chance that of the 7 ducks we select, at least 2 of them